All right, and so I now believe that anyone viewing the video lesson at this point is ready to find out how to find a maximum and minimum value, because all that foundation I've shown you is now going to be used to drive into a maximum and minimum value problem like that. Okay, so now let me, and it won't, once you've built that strong foundation, it won't take too much to understand what a minimum and maximum value is. And so let me now bring you into the other board of mine right there, and we are going to reconstruct a hand sketch version of the graph again. So now any function, okay, any function has a graph. Let's say, so now I have a graph with ups and down, things like that, okay, and it doesn't even have to be that many. But so now you're starting to see in the way how I call these things right before this point, and there are these points where I so-call the turning points, okay, the turning points, because the function was what. So in this case, in this particular graph that I was drawing, then the function was first starting out rising, right, and then dropping, and then drop to a bottom peak, a real low, and then hits back up. So there was falling, there was rising. That's why these were back then referred to as the turning points. So these are turning points right here. But now if you're having a closer look, and of course it's just the way how I have to explain these things, then these turning points happen right at those changes where we change from rise to fall, or from either from fall to rise. So it's just the way they are. So in other words, these turning points, or I try to avoid using this term too earlier, but now it's time to say that these are the peak points. These are the peaks. So you got a peak here, you got a peak here, a bottom peak, you got a high peak, you got a bottom peak again. We got all these points all over right there. And so see, so now by simply looking at it, your natural visual sense here can tell that, hey, at least this point here is the highest. Now, not the let's be a little more clear here, but it's the highest, but at least in some interval near it, right? So of course I'm not saying it's the absolutely highest yet, okay? But it's at least in our natural sense right here, the natural visual sense, then we can see that this point here, because it's a peak, so it's the highest in some interval nearby. And I didn't get anywhere precisely about where is considered as nearby yet, but we will get to that. And then this point here, your own natural sense, your own natural visual sense can tell that it's the lowest in some interval nearby, maybe somewhere like that. And everything right now is completely abstract right there, but you will understand what I mean by that. It's at least in some interval around that, nearby that, and this point is the lowest point, okay? And then we have another point being lowest, but lowest in its nearby interval. Okay, in some more advanced math course, we refer to these as the neighborhood intervals right here. But we will get those. And so we got a high peak here, and another high peak there. So these are, the highest point in some interval nearby. And this is also a highest point in its own nearby interval. Okay, so now, ladies and gentlemen, it's the idea about a maximum being highest, or being the lowest, lowest. We refer to them as so this is maximum, okay, and this is minimum. Okay, so now let me now give a brief understanding of what maximum and minimum means, first of all. So a maximum value of a function f of x, a maximum value, and a lot of time for short it's just a habit right here, but let me correct that. A maximum value of f of x, right, is the value f of c satisfying the function itself is less than or equal to this f of c. Okay, And that's the idea right there. So the function will be less than or equal to this f of c right here. So this is what I mean. And of course, I only show that brief understanding. See, if this is the value c, okay, this is the value x equals c, then the function is less than or equal to that, because that's how we calling that highest. So highest means when it reaches to that, it cannot go higher. Now, of course, I'm about to drive everybody's understanding into local, the kind of highest within its nearby interval. So we'll get to that. But right now, the basic idea about being a maximum is that it is a value that we can, as long as we can recognize a value on the x-axis that cause the function output to be, you see, anywhere else it's less than or equal to that function output, and that's what maximum value is. Okay, so a maximum value of f of x is, see, this is in the form of a function output right here. Is f of c satisfying f of x is less than or equal to, indicating that we can reach to that. We can be equal to that highest value. But otherwise, other than that, it has to be lower. And that's the whole point of being a maximum. Okay? And so, in that same way, and as I said again, this is only a brief, understanding. So it doesn't have to be, I'm just opening up your understanding, so it doesn't have to be too precise yet. And we will get to as precise as you can very shortly after this. And so now, similarly, a minimum, okay, a minimum value of a function f of x is some f of c value against some other f of c. It doesn't have, it shouldn't be the same c here, but I just happen to use the same notation. So f of c, some f of c that's satisfying now this time the function must be greater than or equal to f of c. So either it's equal c or being above c. That's why it's the lowest. Being the lowest, anywhere else is either above or getting lowest, there is the lowest. Okay, it cannot go below. And that's why it's called a minimum value. All right, but now we will get more into the details here. Here is just a brief idea into understanding what it means by being a maximum and being a minimum. So I'm going to get back to the other board and now introducing further terminologies right here. So as you have already seen, these are the peaks. So that makes sense to be regarded as a maximum because you see, at least in some nearby area, then we hit to there is the highest value, the highest outputs, and then anywhere else it's just lower. Okay, or like say this point right here is, anywhere else it's going to be higher than that. At least in some interval nearby, anywhere else it's going to be higher than that. This is the lowest point vertically in that some nearby interval. Okay, and the same way with that, and the same way with this. This is the highest, but only in its neighbor, in its nearby interval, some nearby. And I haven't been clear at all. So some viewers might start getting frustrated with, gosh, where can it? How can we find those nearby? And you will get to that. And this bottom one right here is being also, it's a minimum. Okay, and the graph can tell that it's a little higher than the other one, but at least this is minimum in its nearby interval. And so that's why. So now these are the minimums and these are the maximum. Yes, I agree. So allow me to notate like this. So we have maximum at here and that point. So those 2 points that I point the arrow to, those are the maximums. Okay, and then these two bottom peaks right here, we can refer to them as the minimums. Okay, and so we got a minimum here and another minimum here, and it all depends on how your function is. It could be having a lot more turning points. Okay, and so now, but now it's time to unlock that little thing right here that I was saying. You see these maximums or these minimums right here that I was referring to, I keep using the term, they're only maximum in their nearby interval. Okay, so this maximum is only maximum in its nearby interval. It's probably not the highest one out of all, but at least now here's the term. I might have to rewrite this word because I need to add in another word here. So we got a maximum being here and being here. Okay, but now this maximum, as I said, it's only maximum. These maximum is only maximum in its own area nearby. So now the formal term for that, it's a local maximum. Okay, and sometimes we can also refer to these as the relative, the same as a relative maximum as well. It's the same meaning. So local maximum or relative maximum, it refers to the kind of maximum that it's only true in a certain nearby interval around that. So this is a local maximum in a sense that yes, we can find. So now I'm starting to get a little better we'll start getting a little better when I say local or relative maximum or local maximum or nearby. It just means that there will be a certain interval where this point right here is the highest inside of that interval. Okay, but not for the entire graph, not for the entire function. Okay, so same way here, this point now, these 2 points right here, they are minimums. Okay, but they are not the really the lowest out of all. So now we can call these this is the local minimum. Okay, local minimum, or we can also refer to these as the relative minimum. Okay, and MIN is short for a minimum. Okay, and just like that again, how nearby is good enough? That's not the point. It's just that as we call them the local minimum, that means there's a certain interval. There will be an interval around that, so that this point is solidly the lowest in that nearby interval. Okay, and the same way with this. All right, and so now we come to it's still not going to get too clear yet. Okay, it's still not getting too clear yet, and especially I advise that don't get too worried about how near is called nearby. But now I'm going to keep improving the definition here. So the first the first definition earlier wasn't too clear, and so now I'm going to say a local, or some other textbooks refer to this as relative. Okay, so a local or relative maximum of f of x is a value f of c. Okay, is a value f of c satisfying f of x, just like earlier, either less than, generally the function itself is less than or equal to this value f of c. But now I'm adding in a little modification for x nearby. Okay, so nearby, so for x nearby c. Okay, or we don't have to use fancy term, just for x near c. So c here is a specific value. So let me quickly do that, show that demonstration again. So c can quickly be a value here. And so for x, for any other x generally nearby c or near c, then the function will always stays either below or the highest is it hits that high peak, and that high peak is f of c. And that's the whole point, and that's what it means by a value f of c satisfying that the function value in general less than or equal to that f of c, but locally means only for x near that particular value on the x-axis, x equals c. Okay, and so another way of saying that, it's a relative maximum, and relative means it's only a maximum relative to its own area, its own zone. Okay, and so the same way, I'm a little short of the board space here, so I am going to erase part of my definition and to change to the other definition. So now I'm going to modify this. So that's a formal enough definition for what a local maximum is. So now I'm going to call that, how about a local or relative minimum. All right, so a local or relative minimum of a function f of x is a value f of c that's satisfying. Now this time the function value in general, f of x, must be anywhere above or the lowest is equal to f of c. And that's what it means by being a local or relative minimum of the function f of x. And so again, allow me to quickly illustrate that here. If we can look at this local minimum through the picture right here, if we see that low bottom peak right here, if that x value where we reach that bottom is x equals c, then yes, the function anywhere else away from c, then the function value is above. So this is f of c. And so the function value is above f of c, higher than or at least. The least is only f of c. Okay, and then anywhere else is above that. And so that's why, back to what I said right there, the function value is greater than or at least, the least is equal to f of c, but valid only for x near x equals c. So of course we're still not clear about how near is near, how close is considered as close, but that's not the point. The point here is that there will be a definite interval where there will be a certain interval where it is truthful about this. Okay, and that's the point. And as a matter of fact, we will almost never have to find where's that near interval. Okay. All right, but now let's have a closer look. Because just beating around the bush with the definition doesn't help us knowing how to solve the problem. What I want everybody to understand further and to have a little closer look into these peaks, these what I so call now the local or the relative maximum or minimum. Now this is how I see it. If we're looking at these local maximums or these local minimums, then these are just the turning points that we have spent some time looking at earlier. These turning points here came right between switching between an increasing and decreasing, or switching between a decreasing to an increasing. It's just the way it is, okay? But now a little more straightforward into my point. These are right at the point where, so these are now, we call them the local maximums and the local minimums, but those are just right at those points where we have horizontal tangent line hits right there, okay? So be careful. Just because we have horizontal tangent line doesn't mean we have to have a maximum. Nope. See, horizontal tangent line, but it could be maximum or minimum. It could even be something like this. It didn't happen in our graph yet, but we can have a graph that's in a waterfall shape like this. Okay, tangent can be horizontal right there. Okay, but a point like that is neither a maximum or a minimum. So my point now is that using the horizontal tangent line is a good way to detect maximum and minimum. But once we have come to those points where we have horizontal tangent line, we have to test further to decide who's the maximum and who's the minimum. You see what I'm saying there? But now one thing we know for sure, those local maximum and minimums must happen at those values where we have these. See, these are critical values. See, these are all the critical values, horizontal tangent lines. All right, so now after having some clear understanding, then we have a theorem. Okay. So this is what the theorem is stating. So a theorem is a proven truth. Okay, it's a truth that was mathematically proven by the past mathematician. So if a function f of x has a local minimum, and the same with local maximum, or that's what I'm saying, a local minimum or a local maximum. Either one can happen there. Okay, having either a local maximum or local minimum at a value x equals c on the x-axis. Let's quickly look back at. See, if we have if our function hits a peak, a high peak or a low peak, that's what the theorem is starting to say right there. At some value on the x-axis, here's at x equals c, here's at x equals maybe x equals b or something like that. So at any value on the x-axis where the function hits to either a local maximum and minimum or minimum, then so if we know that we hit to a local minimum or maximum at a value x equals c, then it must be true that f prime at c, okay, equals and let me add in a more powerful term here, then either f prime at c equals 0, that's 1, or f prime at c is undefined. Okay. But now, if we're having a closer look into this, f prime at c equals 0 or f prime at c is undefined. Does that look familiar to something that we have done previously? Okay. So wait a minute. This is actually the requirement for being a critical value. So now simply immediately after writing this down and I triggered your attention that, hey, this is the requirement based on the definition of what a critical value is. Any one of this is a requirement of being a critical value. And so now all of a sudden we realize that this theorem can be written in a better form. Okay, so now I'm going to erase all that because that was the original idea of this theorem. But now nowadays, this is how it says here. If f of x has a local minimum or a local maximum at x equals c, then x equals c must be a critical value. All right. X equals c must be a critical value. All right. And so now this theorem actually now gives rise for us a method for us to detect where we can find local maximum or minimum. Okay, so here's the idea. Because like I said, maximum or minimum can happen if anywhere it happens, then it must be among the critical values. That's the important. So up and down, see? If we recognize through the graph or whatsoever reason anyone telling us that we got a maximum or a minimum at a couple places, then for sure this theorem says that those x values must be critical values. And so in that way, what I was in the middle of saying now is that it gives us a way to detect, because now simply the first thing to find local maximum or minimum, the first thing is simply get straight into finding critical values, as many as you can, finding all critical values of your function. Because now once we have tracked down all the critical values, then among those critical values, some of those could be maximum and some of those could be minimum. Okay, but for sure, maximum or minimum, local maximum or minimum must only happen within the critical values, within at with those x values being the critical values. That's the idea about that, and that's how useful this little theorem is. Okay, and so now after so much explanation right here, let's get to it. Let's really do some example and really get the problem nailed down right here. All right, and so now I am going to get into example 3 right here. And let me look into my problem bank right here. So this is the main instruction, the main instruction of the entire example 3 right here, and we will be given at different functions. So we want to find all maximum, and allow me to use the shorthand writing right here is max, max, just for maximum value. So find all maximum and minimum. So another shorthand writing min is for minimum value. So find all maximum and minimum values. Okay, maximum, minimum values of, and now, of course, these are, I have to emphasize that term, the local maximum and the local minimum values, okay, of the given function. And so I'm leaving it hanging right there. Okay, and so now, question A, part A of our example, about f of x equals 2x cubed minus 3x squared minus 12x, okay, and plus 1. Wait a minute. Isn't that it's the same example, again, the same exact function we've been doing since example 1, part A, then we moved on to example 2, part A, okay, and now I'm using the exact same function again, okay, for us to find all local maximum and minimum. You will be understanding my intention as soon as we start getting into it. But right now, if I want you to also recall that throughout the entire example 1 and entire example 2 where we have seen this function, I never asked anyone to really, and I didn't even bother showing the actual graph of this, because that's the point. Now with the math, with just the calculus, without the graph, and you don't need a graphing calculator, we can detect all of the local maximum and all of the local minimum values of this function. Okay, and that's the whole point right there. And so now, just as what I said right before we really get into this example, then the key things that we need here is to find out all the critical values, because just as the theorem was stating earlier, all local maximum and local minimum values only happens around within those critical values. So our first thing is to detect all of the critical values of any of our given functions. Okay, and so that means the reason now that I brought it in the exact same function where we have already worked with in the earlier problem, because I don't want to waste any one of my viewers' efforts to redo. But you are more than welcome to retry these things if you are sort of jumped in the middle of the video. But so, carrying out from past example, then critical values for this particular function are x equals 2 and x equals -1. Okay, so this is all we have for the critical values, and we got 2 of them. Okay, but so now I want you to start realizing this. So these are all the critical values, but do not just rushly say, hey, this is the maximum and this is the minimum. Neither the other way. So at this point, we are still very unclear whether this is a maximum or minimum, or whether this is a minimum or maximum. We're still very unclear about that. But I'm sure, I can guarantee you that all the local maximum and the minimum happens within these guys right here. And that's the idea. And that's why I'm using that term, within these guys. It won't happen anywhere outside of these 2 points, of these 2 x values on the x-axis. And so here's the way to detect. Now I'm going to spend some time erasing my other board. Okay, so let's get to it. So this is what I'm doing now. I am going to get back to our favorite sine chart, which we also have done already. So back on the sine chart that we have seen in example 2. So the sine chart for this particular function here is going to be, once again, imagine this is the line of real values. Okay, -1 comes first on the line, and 2 comes somewhere. And then we have seen the sine chart back in example 2 already. So allow me to pick up the fast pace for this sine chart. So this is the interval where x is anywhere, see, less than 2, greater than -1. This is for x is less than -1, and this is the interval for x greater than 2. And so if you want to see how I got these decisions right here, then you can go back and view example 2. Roll back to example 2, see how I came up with these. Now I'm just briefly recalling the table. But this row here is for the sign behavior of our f prime right here. And this row down here is the actual increasing or decreasing behavior of our f of x function originally. Okay, and so according to the work that we have already done, and that's why I'm saying once we can use the same example, the same function from the past example, then we save for ourselves a lot of efforts right here. So all that useful information come back here. So we already agreed that we had positive sign for f of prime of x in this first interval. Okay, and we had a negative sign for f prime of x in this middle interval for x values anywhere between -1 and 2. Okay, and you can roll back to the earlier part of the video in example 2 to see again how I had that decided there. And then this last interval here is a positive interval. I mean, it's the interval where our f prime will turn out being positive output value. Okay, so positive slope of the tangent line, negative slope of the tangent line, okay, and positive slope of the tangent line. So earlier in example 2, this is what I did. So I made a conclusion that in this interval for x being less than -1, then my function is increasing. That was the term I was using, because that was the answer that example 2 was looking for. But now just keep in mind, in this example 3 right here, then looking for increasing and decreasing is not the ultimate goal of the problem. So here I just having an understanding that our function must be increasing in this interval. I recommend doing an extra step, but optional, but extremely important. I mean, it's extremely useful. Increasing from the left to the right. I'm going to draw an arrow kind of going up like that. That's a good way. And you see, in practical situation, when you are doing a fast work, you can entirely skip the word increasing. You can just simply use an up arrow like this. From the left to the right, a rising arrow like that. It's indicating your function is increasing. Okay? And so in that same way, in this interval, the function is decreasing. Okay? DEC is for decreasing. And then if we are making a quick arrow sketch here, the function is going to have to drop like this. From the left to the right, it's getting lower. That's why my arrow is pointing down. Okay? And so now the function is increasing back again. The function is increasing. So the arrow, if we would draw, it's going to have to do like that. Now, I've seen some textbook authors or some teachers explain with students increasing but by drawing arrows like this. But I decide not to teach my student this way, because if we're drawing an arrow that's just simply too vertical like this, then the student actually will lose the sense about increasing or decreasing, because here I'm using slanted arrows to indicating that we always view things from the left to the right. So it will be easier for student to see and to catch that nature about, from the left to the right, the function is getting higher and higher, or here from the left to the right, the function is dropping lower and lower. Okay? And so that's why I'm not using this symbol. You can decide that for yourself, but it's all about you assisting yourself like that to keep things clear. And so now, do you see that? So right here at this x equals -1 is a critical value. Okay, but now we are ready to make decision right here. Think about that. See, I call that it's a turning point. So what does it mean by the turning point? The function was turning from increasing to decreasing, was rising and turns to falling. See, my hand motion was doing it, rising and falling. So what can you say about this? Yes, this has to be, at this point right here, it has to be, we must get a local maximum right here. You see, because the function was rising and hits to a max. Where is the max? The max is at this critical value, x equals -1. And then after that instance, it's going to start dropping down. It's going to start dropping. And that's why now we have all of our legitimate reason to say that at this critical value, now I'm saying at x equals -1, this critical value, our function achieves or hits to a local maximum value. Okay, and so now moving on to the next critical value. So we already had a decision on one of our critical value. Let's move on. And so please do not rush. Just because you have already made a decision on one of your critical values, that doesn't mean the other one have to be the opposite one. Okay, eventually I will have some students making that mistake. Stay away from that. Every critical value you just have to do that careful check. Okay, so what's the check here? The check or the test here? The test here is that anytime your function switches from increasing to decreasing, that critical value in the middle, in between, has to be a maximum. And now the other way around. So now you see right at this critical value, x equals 2, your function switches from decreasing to increasing. You see my hand motion as well, and I'm trying to follow that arrow in description right there, falling and then rising. So there has to be a minimum point. So this point here, now I call that it's a local minimum. Okay, all right. And so that's how we detect a local maximum and a local minimum in our problem. And so now we are ready for answering it. So the chart now gave us a way to detect already, but now we have to make our answer here formal. So it's now time for me to get really detailed about this. But anytime it comes to doing a maximum or minimum value problem, you got to be extremely cautious in the way how your instruction is. Find all local maximum and local minimum values. So this kind of problem is actually behind the scenes. You actually have to answer two things. Okay, for either one of them, local maximum or local minimums, you have to first answer where is the maximum. It's sort of like you're asking yourself, where is the tallest building in the city? Okay, where is the maximum value? Okay, so for that, here we're saying it's at x equals, the Sine Chart was indicating for us at x equals -1. That's only where we can get our function to as a local maximum. And I should have written where is the local maximum. Okay, and now that's only one half of that answer for the local maximum. Okay, that's only one half of that. After you know where to locate your local maximum, then the next question really is, how high is it? That's the other part that a lot of times when you're working with a maximum or minimum problem in general, no one will be precisely clear for you. So it's your responsibility to always know that there are always these two questions. Where is the maximum and how high is it? Okay, unless some problem being specified otherwise that, hey, only find which x value gives you the maximum, then you have a nice problem. But in a problem like this, and I purposely gave anyone viewing my video an unclear instruction problem so that you have to understand it's your responsibility to be able to answer both little questions just to answer the maximum. Okay. And so now back to what I was saying. See, we already answered where is the local maximum. So now it's the next thing is how high is it? Just like what I brought up earlier about the building. Where is the tallest building in the city? Well, so now maybe you say it's anywhere here, like the First Street, or whatever in downtown, or whatever. That's where you can locate the high value. Okay, but now when you get there, the next question: how high is it? Like what, 500 feet high or whatever? So that's what it is for this. And so local maximum, where is the local maximum? We answer that it happens at that critical value x equals -1. But now how high is it? How high do you think that is? We are now going to substitute the critical value x equals -1 into the function, not the derivative, into the function. And so now I'm going to have to step away a little bit for a quick calculation. All right, so now I have a value. So first of all, let me lay down the calculation step. This is what it is. Remember, your function is, we're substituting the critical value into your original function. So now you need to do, you need to do 2 times -1 cube minus 3 times -1 square. I'm a little short of space, so allow me to write in a lower line right here so I can have more space. So f at -1, that is 2 at -1 cube minus 3 at -1 square minus 12 times -1 plus 1. Okay, and then after all that calculation, my answer came out 8. So this is how high our function reached at x equals -1. Okay, and so here, because I'm giving instructions, so I have to write down this question. But when you're actually doing your work, nobody has to write down these 2 lines right here. Where is the max? It's your responsibility to find where the maximum value is, and after that, find out how high it is. But you don't need to write down these 2 questions right there. They are just sort of like your goal right there. That you just gotta know it. Okay. So now we only answer half of our question here. So each of the half of the question got a 2 subparts of that, right? But now I'm gonna move on to the other ones. So this is now about the minimum. So back on the sine chart, we already knew that we decided that we had a local minimum at x equals 2 right here. So now for the local minimum. So once again, for that question, where is the local minimum? Okay, that's question right there. And so now our answer. The local minimum is happening at x equals 2. X equals 2. Yeah, the other critical value. And now once we located that, where's the lowest building? Where's the shortest building in the city? Maybe the corner of Main Street and First Street, something like that. It's about we locating it. Okay, and once we located it, then how low? Okay, how low? Okay. Or this is let me change my wording a little bit. How low does it get? Okay, that means how low does the function value get, or how low does that building get? Okay, so to get how low the function value is, once again we have to take the critical value and substitute that into our actual function. And so now it's 2 times 2 cube minus 3 times 2 square minus 12 times 2 and plus 1. Okay. And so allow me to step out of momentarily and do another quick calculation here. All right. And I might make some calculation error, but that's okay. You will learn the generality of this problem. But my answer here came down to -19 right here. Okay. And if this is a face-to-face class, then I invite my students to work along and check my calculation errors all the time, because I'm in the end a human being too. All right, so that's how we're answering where we can find the local minimum and how low it gets right there. Okay, and so this is really tearing it down to every single details, but normally when you're just simply doing your own work or it was just me doing it on my own without the teaching part of it, then I'll just simply, this is the most standard way how the other people are doing it. We can just say we have the maximum value, right, equal to 8, but it happens at x equals -1. You can also be clear that this is a local maximum, okay, and the value there is 8, and it happens at x equals 1, and then we have a local minimum, okay, and there are quite a few different ways of how we can indicate our final answer. It just doesn't have to be as detailed as how I wrote down earlier, at x equals +2, and that's this way of expressing your final answer is perfectly good enough, okay, for any one of us. All right, so that's how we find local maximum and local minimum values of this function, okay. And so now, before I move on to another problem right here, and we're still in example 3, but let me bring up a terminology here. So as a matter of fact, the truth here is I call it a sine chart because this is the idea that was, you start learning this idea since your pre-calculus course. And trust me, any calculus students will have to go through a pre-calculus course. And this idea using a sine chart, now a sine chart is not only used for checking sign of derivatives. That's to be clear, but we use the sine chart here cleverly to check our signs for derivatives so that we can detect increasing and decreasing interval. And so I keep using the term detect, but in the end, the whole sine chart here is to test where we have increasing interval and decreasing interval and increasing interval. It's actually a test. We test which interval around all of these critical values we have found to be increasing and decreasing. And so, this test is heavily based on the behavior of the first derivative. Okay, and for that reason, the idea of using sine charts to test or to detect increasing and decreasing intervals, and so that we can eventually come down to deciding where we can have local maximum and local minimum. This whole picture about using the sine chart table is being referred to as the entire work that we do in here with the table, all the way to decide local maximum and local minimum. We refer to this as the first derivative test. Okay, and that's the whole process of using the sine chart here is being regarded as the first derivative test. We test for increasing and decreasing interval so that we can decide where our local maximum is and where our local minimum is. Okay. All right, and let me now really show you the graph for f of x function, because believe it or not, we've been working on this function, f of x equals 2x cubed minus 3x squared minus 12x plus 1 for the entire 3 different examples, and we've made a long way into this function. But surprisingly, I haven't shown you the graph of this function at all, because I want you to be able to, I want to show you the fact that just doing the math, we can get all of these fascinating answers regarding our function. But now, let's bring up the graph so that you can see how consistent our work with the math, with what the math came out right there. Okay, so now on my computer screen here, with the blank graph right now, this is going to be your function f of x. This is the graph for, okay, so ladies and gentlemen, this is the function for 2x cubed minus 3x squared minus 12x plus 1 right here. And so just like how we found it, we found 2 critical values. One of them is at x equals -1, and the other one is at x equals 2 right here. And so right there, in looking at the shape of the graph itself, you can see that it's rising from the left to the right to that point x equals -1 and hits a high peak right here, and that's why my answer came out as a local maximum here. It was f of -1, b equal to 8. And then at x equals 2, we have another critical value. And right here now, after doing the first derivative test in example 3 just now, then we have we concluded that this x equals 2, this critical value gives us a local minimum. So the coordinates here is reading our local minimum hits down to as low as -19. And that's the graph for our function as I said. Okay, and so we got increasing and decreasing and increasing all over in this function. All right, and so let's now look at part B of our example. And so I have purposely spent a lot of time to explain in details how we can go through the sine chart, and especially came to that decision about local maximum minimum. But now once anyone viewing this video has gotten pretty engaged into the kind of work here and getting yourself in gear, then I can now start picking up pace a little bit. Okay, so I'm going to take a minute or so to erase my board. All right, so now I am going to look at, let's find the local maximum, all local maximum and local minimum values of our function in part B right here. Let's look at what I have in my problem bank right here. How about cube root of x again? So that same function g of x we worked throughout all example 1 and example 2. Part B correspondingly, all correspondingly. So here's part B of our example 3. We want to find the all local maximum and all local minimum value of this function. Okay, so now recall that we already came to concluding that this function had, from earlier example, we had a critical value, and actually for this function, if we recall from example 1, then we only had one critical value right at x equals 0. But that was because, remind yourself, that was because the g prime at 0, right, is undefined. The value of g prime at x equals 0 at this critical value is undefined, and that's why we actually concluded that this value was a critical value, just straight out from the definition of what it means by being a critical value. Okay, and then let me now briefly remind anyone about our past table sine chart for this function. So for our function, we only had one critical value, so that means x equals 0 is here, and think about this line here is the line of real numbers. So this is x is less than 0, and this is x, all the x value greater than 0. Okay, and so according to our sine chart that we have already found, here I'm just reminding, so g prime of x will be a positive, we have a positive output in the interval where x is less than 0. And also recall for yourself, g prime of x will also have a positive sign, okay, for this interval x greater than 0. So that means as far as the function g of x itself, it is increasing in this interval. And so learning from the notation I introduced, learning from the symbol, from the style that I introduced in part A, then I'm using this rising arrow over here from the left to the right to indicate that our function is increasing. Okay, so, and in this next interval, the function is also increasing. Okay, and so that means as far as the arrow, I'm also using another arrow pointing up like that. And this is where, so right now, see, x equals 0 is a critical value. It is a critical value. However, as far as, is it a local maximum? No, because it's not this place right here. It's not the switch between. I mean, if If it's a rising and switch to decreasing, then it's a maximum. Or if it's a decreasing and switch to a rising, then it's a minimum. But this is neither, because see, in the two intervals in the end, even though we have a critical value that breaks our entire line into two separate intervals, but the two intervals are doing consecutively, they're both doing rising up, okay, in the same way right here. So this critical value, our conclusion here is neither, and neither maximum, right, nor minimum. All right, so neither one of those. Okay, so it does happen out there. So I purposely I prepared this example so viewers can understand that there are cases out there where a function reach to having a critical value, but sadly it's neither a maximum or minimum. And there are other cases out there where we run into critical values like this, where it's neither a maximum or minimum. So just because we have a critical value doesn't mean we're going to have doesn't necessarily mean we have to have a maximum or we have to have a minimum. Okay, and that quick little example is right here. And so in this case, now how do we conclude our final answer? The function here is looking for find all local maximum and local minimum values, and our only critical values fail to be either the maximum or minimum. Then we just say now we have no local maximum, okay, and no local minimum. Okay, so that's all we can answer. All right, and so again, we have used this function g of x for quite some time as well. We started using that since example 1, and then we moved on to example 2, and then now here we are at example 3 that we ultimately used. And by the way, I recall again the entire process that we used the Sine chart. So it was a long process I built for my viewers since example 1 up until this point. But the whole idea about using the table to test for whether our critical value can be a maximum or minimum or even neither like this. This is the first derivative test right there. Okay. And so now allow me to quickly show a graph. It's time that I let everybody know what the graph of this function looked like, so how it can be consistent with the fact that it's increasing and it's increasing again, and this critical value, it's a critical value, but it's neither a max or a min. Okay, so why is that? So let's find out. So all right, so this is my blank graphing screen right here. So that function we've just now looked at, f of x g of x equals cube root of x is here. All right, so this graph here in blue. So first thing caught my attention. See, we can have a tangent line right here. So right here, the y-axis itself can be used as, we can regard to that as a vertical tangent line. So this function, it's just the way it is. It hits a vertical tangent line right at x equals 0. And so because of that, when the tangent line is a vertical tangent line like this, we can draw that vertically. It exists. But as far as the slope, the derivative, it's an undefined derivative, or we have a non-existing derivative based on the limit definition. Okay? And so because of that, this value qualifies, x equals 0, this value qualifies to be a critical value. However, right here, it's not a maximum or minimum. And your eyes, right at the moment you're looking at this graph, you can see for yourself that it's not a maximum, neither a minimum. Okay? And here's how, and here's what explains, and being consistent with the Sine chart right here, the function is rising, or in other words, increasing and increasing. Okay, and to wherever that is for the critical value, and it continues increasing and increasing. Okay, and that is the reason why our Sine chart was indicating in that interval x less than 0, our function was increasing, and it continued increasing in the other interval. Okay. All right, and so now at this point, let's head out for part C of our example 3 right here. All right, so after taking some time erasing my board, here's our function given in part C. So our function here is, how about h of x, okay, equals e to the x plus e to the minus x. And here it is again, I'm using that same function again, h of x, from all the way from example 1 through example 2 that we already had a sine chart for it. And here we are at the same function to find a maximum, local maximum and local minimum of this function. So the key thing we need here is, once again, the critical values. We first need to detect all the critical values. So example 1 showed us all the critical values of this function. So if you're unsure how I got this, you feel free to roll back to the earlier part of the video. But the only critical value we have here is x equals 0, and we actually solved for it. Okay, we found this value by setting the h prime of x equals 0 and successfully solved for it for this value, and it's the only critical value we found. Okay, and no undefined value or anything or whatsoever like that. So now as we came to this point, again, let me move on to the other board and let's construct a sine chart here. And this is what we found for our sine chart according to example 2. On the line of real values, 0, our only critical value is there somewhere. So once we place it there, it breaks the whole line into 2 separate intervals. And so here's our table. Okay, one row is for h prime of x, and one row is for the behavior of h of x. And so this interval is x less than 0. This interval is x greater than 0. And you can see that how I have already started picking up pace right here. And so trust me, once you are fluent, after viewing thoroughly this video and fluent with that skill, you can even work on these steps a lot faster than how I do it up here. Okay, so now the sine chart here from example 2, we found out that we had negative sign for this interval when x was less than 0, when x was negative. So our h prime of x was negative sign in this interval, x less than 0. And then the sine chart was saying earlier in example 2 that this h prime of x was positive sign for the output when x was greater than 0. And so that consequently led us to this conclusion that our function itself, h of x, was decreasing in this interval for x less than 0. And so now with the arrow notation, I'm drawing this arrow that's dropping from the left to the right, but falling. Okay, and so now same way, similar arguments. Now since my h prime of x has positive sign output right here, then the function h of x itself must be increasing in that interval, and we have already seen this in our example 2. But now using the arrow notation, I'm indicating that our function is increasing from that. Okay, and so now in that way, this value here is now clearly, this critical value is clearly a local maximum, local minimum. Okay, because now how can we decide like that? The function was at this critical value, it was a switch. It was the switch between decreasing and turning back to increasing, and that's the reason why. Okay, so after that decision, let's now move back to the other board and write down our final conclusion. So here's the thing. So, but ultimately, we already decided where we found the local minimum, right? But we need to really answer it. So first, I am going to substitute. So allow me to use the fast pace right here. Our function is h of x being this. So I am now going to substitute the critical value x equals 0 into the function. Okay. And so that gives me, so this is the critical value. The x equals 0 itself is critical value, and now I'm substituting it into the function to find out how low it is. Okay, because we only found one critical value, and that was a local minimum. So for this function, I guess no maximum. Okay, and I'll get to that later. But e to the 0 plus e to the minus 0. Okay, e to the 0 equals 1. E to the minus 0 also equals 1. Okay, so our final answer is 2. So this is what I'm saying. We have a local minimum. Okay, a local minimum. And that value, so this is, I refer to the value, the local minimum value equals to 2. Okay, it's happening at x equals 0. Okay, that's my answer right there. Precisely answer how low it hits, okay, and where that's at, where that can be located. Okay, and so that is. But now, as far as about the local maximum, then we don't have any. So I'm saying no local maximum. Okay. All right. And so now, again, allow me to prepare my computer screen here and quickly show everyone the graph of that, of our function here. Okay, so here's on my blank graph again. Okay, so the graph for our h of x is here. All right, so this graph here in green right here, it looks almost like an x squared function, but it's not. Okay, it looks like a quadratic function, but it's not. It's not a parabola. It's just some shape like that, but it's not that quadratic parabola. That's what I mean. Okay, and so yes, we only have one peak ever, and so that happens right at 0, 2 here. So 0 is where we reach the peak. Okay, but 2 is how low that peak hits down at the bottom right here. Okay, all right, and that explains everything about our graph and how it's consistent with the sine chart that we've seen. It was decreasing and hits to a bottom and increasing after that. All right, so now I'm going to bring up another example where this time let's really look at one completely brand new function, and we're going to work through all the steps from the beginning to the end so that you can see, how and kind of comprehend the whole idea right here. Okay, and see how on standard the steps being carried out into different stages. Okay, and for this problem, my advice here is that stay as close as possible to how I structure my example. So I started out with example 1 for a purpose, and started out with example 2, and now arrive at example 3. So those are actually 3 main stages of a general maximum and minimum problem. Actually, it was my entire intention behind the scene for all that. So now we're looking at example 4, and I think I only need to give out one example, and we should be good for everything. Okay, so let's call that now example 4. So let's look at our function here. How about f of x? Okay, so find all local maximum and local minimum values of our function being. Okay, so x to the 4th minus 4x cubed plus 10. Okay, so it's this time, just as I promised earlier, it's a completely brand new function. So there's nothing from the past to reuse. So we have to start everything from scratch. Okay, so think about how it happens throughout our 3 examples earlier. Then example 1 was entirely about finding all the critical values. And that's always like the first thing to do, because it built into eventually finding local maximum and minimum values. So here it is. when we actually add one problem where you really are on your own finding a local maximum and local minimum value, or find all of them, then your first step is to find all the critical values, because we have to find all the critical values because local maximum and minimum only happen within those guys. Okay, and so now gladly your function is a polynomial, so we have no worries about undefined values or anything like that. And for sure the derivative will be a polynomial, sort of like just a quick plan ahead. Okay, but anyway, we have to find our derivative, f prime of x. So first term of the function gives me 4x cubed. Okay, middle term of the function gives me minus 12x squared. Okay, and last term of the function is a constant, so taking the derivative, it gives me a 0. So this is our first derivative. Okay, and of course, needless to say, the process I'm going through right now is being referred as the first derivative test. So with that name being said, it makes sense that we got to find the first derivative as the first thing. But now once we have found our first derivative here, then we really are getting into finding the critical values. So now I'm going to set 4x cubed minus 12x squared to equal 0. Actually, the main goal is set f prime of x to equal 0. And that produced this equation for us. And now we're going to solve this equation for 0 over here. Okay, and so now solving this equation for 0. I'm erasing part of that there to keep the board a little bit clean. Otherwise, it looks too busy. So we got a common factor for, and when it gets to something like this, we have to, most of the time we stay with the factoring method. So I can quickly see that I have common factor being 4x squared. I can freely pull that out. 4x squared can be factored outside of the parentheses, and what I have left behind here is going to be just simply x minus 3, okay, equals 0. And we now have completely factored our left-hand side of the equation into a product of two terms. Okay, and so now when it comes to solving that, then we turn into having, okay, and I leave the algebra for you, because at this point allow me to start assuming that you have reviewed enough algebra and start getting somewhere more comfortable with algebra. So x equals 0 is one solution, and x equals 3 is another solution. So we found two solutions, two x values where the derivative f of x equals 0. Okay, that's what solving equation is for. So just think about back in those days when you were solving an equation back then. I mean, solving an algebra equation back in your algebra course, and you felt deadly that why do we have to keep spending so much time solving an equation? But it equipped you back, those courses equipped you these skills so that when you go to your calculus class or even any higher courses, those are your essential equipments that get you through the problem. Those are your tools that get you through the problem. So promise me, for any viewers, if you feel unsure with any of these, make sure you review your algebra or find a way to get a hold of me so that I can clarify any of these for you. Okay, so now you found your two solutions to this equation, and so now you can conclude that your critical values, okay, your critical values are x equals 0, that's one of them, and x equals 3, that's another one. But I don't think I need to put these in a box because they're only one stage. So we got through stage 1, sort of like at the end of example 1. If this problem was part of our earlier examples, okay, so we found two critical values, and those are it. And I said a little earlier, I said something about, see, the derivative will also be a polynomial. That's what it is, because our starting function was a polynomial. So when it came to the derivative, it's just the way it is. It became a polynomial. So for polynomial, I never had to worry about having any undefined value for x. So I can just simply go right into that route where I solve for setting the derivative equal 0 and solve for x. Okay, let me now go to the other board and let's get ready for the sine chart right here. I'm going to take a minute or so to erase my board. All right, so now on the sine chart right here, think about the line of real numbers again. Think about the line of numbers. So we found two critical values from the previous step. So now I'm going to arrange all of those critical values on my line. And of course, now I said arrange. That means they have to go in the numerical order. And so 0 is the lower one, and 3 is the higher one to the right-hand side. Okay, but it's just the way it is. It's these two critical values, one being placed on the line of numbers. They're gonna just break our line of numbers into three separate intervals or three separate zones right here. Okay, and so this zone here, this interval is for all of those x values less than 0. This is for x between 0 and 3. Okay, 0 and 3, and this is for x greater than 3. Okay, and so now I am going to get straight into one row for the sign behavior of our f prime, because that's the most critical part, right? That we need to check the sign of our f prime, of our derivative, because that's responsible for tangent, or for increasing or decreasing, or I mean decreasing or increasing. And then the sign of our f prime in each interval individually will determine the increasing or decreasing behavior of our function, our original function in each interval there. Okay, and so now I'm going to start picking a value. Say when x equals less than 0, pick a value for x less than 0. I think in my mind right now I have x equals -1. Okay, you can have other value, but what I'm doing now, I'm going to quickly substitute that into, so f prime of -1. That's my calculation is going to be. So our f prime was 4 times -1. 4x cubed minus 12x squared, so here it's going to be 4 times -1 cubed minus 12 times -1 squared. That's the calculation for that. So this is going to be negative, and I should hold that, it's -8, but I'm going to write the negative sign in red ink. Okay, so what it says to me now is that I'm not too worried about the value 8, because like I said, if somebody else or any other viewer who picked a different value here, as long as the x value you chose is in the negative, I mean in the interval less than 0, then that will work. But what matters is this sign right here. So now it tells me that my f prime will have a negative output value, a negative sign for output value throughout the entire interval for x less than 0. Okay? And so in that same way, now I am going to quickly advance, and you can see that my pace here has already been a lot faster than how I was doing that back in example example 1 and 2 right there, especially example 2. And so now here inside the interval for x between 0 and 3, I pick x equals, how about 1? It qualifies just fine. Okay, so now I'm going to go again, f prime. Okay, I substituted the chosen value to test. Okay, substitute that into the f prime, and so 4 times 1 cube minus 12 times 1 all square, just that. And again, this calculation based on my chosen value for x being +1, and I came out with again -8. -8 again. So that means my entire interval here, my interval anywhere for x between 0 and 3, I'm looking at a negative sign for the function output value. I mean for the derivative, the output sign right there. And now I'm going to pick x equals, how about 4 in that interval for x greater than 3. Okay, and again, any viewer can pick an independent, another value different from mine right there. But now I'm doing f prime at 4. Okay, and that gives me 4 times 4 cubed minus 12 times 4 square. Okay, and now I need to step out for a quick calculation here. All right, so my calculation shows positive 64 this time. Okay, and so now I'm not particularly interested in the 64 value. It just came out because I chose x equals 4, but other viewers who chose with different values inside of this interval, then you will get different value. But what I'm interested in is this positive sign right here. So my f prime here is a positive sign for that. Okay, positive sign for x value inside of any x value inside of this interval x greater than 3. Okay, and so now I am ready to make our conclusion about increasing and decreasing, and I don't even have to verbalize the term here, because you see ultimately this problem is about just to detect maximum and minimum, local maximum, local minimum, and so I don't have to, it's not ultimately looking for increasing and decreasing. So we just find something fast to decide our answer. So this interval, we're going to have a decreasing for our function. Okay? And then in that interval, we're going to have an increase. In that interval, we're going to have our function continue to have decreasing. Okay? And so immediately right here now, we can say that our critical value here is neither max nor minimum. Okay, it's just maybe, and I will definitely show the graph of this function at the end of the example, so you will understand again that other case right here. But so now our function is, it's not, at this critical value right here, it's not doing that switch between one behavior to another behavior, so it's neither. Okay, and now in this interval our function is decreasing, but then according to the Sine chart it's increasing back up, okay, in that interval. And so now this critical value here must be it's decreasing, it's dropping and then drop to a bottom peak and hits higher. So now this is a local minimum. All right, so now we have found a local minimum. Even though we had two, we have found two critical values, but only one of them became a local minimum, and there was and this other one was neither. Okay, and we didn't spot any local maximum at all. Okay, so now let's get back to our other board, and then we're gonna make our final conclusion. So now, as far as, so I'm going to substitute my local minimum, my critical value being x equals 3 into the actual function. And let's do that calculation now. Recall again, and look closely again. I'm substituting the critical value into the function. Okay, and so now it gives me 3 to the 4th minus 4 times 3 cubed. Okay, and then plus 10. Okay, and so now I come down to negative altogether with my calculation here. This time is easy enough that I don't think I need to step away for a calculation, for a calculator. But negative 17. Okay, and so now with that, this is what it says right here. Our local minimum value. This is, see, it happens. This is how low our local minimum value hits, because this x equals 3 at that critical value we hit to a local minimum. And so now I'm answering that question. Our local minimum value equals negative 17, and it happens at x equals 3. That's our answer. And of course, and I don't even think we need to say no maximum or anything like that. Okay, and so that's all we found. Okay, so no maximum. There's a local minimum at x equals 3, and it gets down to as low as negative 17. Okay, and that's how we solve how we find all local maximum and minimum values local minimum value of this function. Now let me quickly prepare my computer screen right here to show everybody the graph of that function that we just now work with. All right, here we are. Let me now turn away to the computer screen right here. Okay, so this is our function x to the fourth minus 4x cubed plus 10 right here. This is it. Okay, and so now let me put in some closer zoom right here. Okay, and as I worry that if I put in too much zoom, then we won't be able to see all of it, because right now it's still not too clear right there. But see, now we have that waterfall nature. Let me zoom in right there at that spot. See, right here it's 0, 10, but we don't need to worry about that point because it's not. You see right there, it's doing. I just now use that term. It's a waterfall from the left to the right. It looks like a waterfall shape right there. Okay, so that point right there, it is a critical value because as far as tangent line, our tangent line will become horizontal right there when x equals 0. But this point is neither a maximum or a minimum. Okay, so that's why we didn't have to worry about that. But we found that, we detected that through the sine chart. But now for our other value, okay, we did hit to a bottom peak right here, and that bottom peak was 3, negative 17, and so 3 was one of our critical value here, and at that critical value we hit to a local minimum here. Okay, and so our minimum value here is being negative 17.